Record on this computer. Okay, that's what I want to do. All right, so I'm recording. We're starting a new topic today, and the next two chapters, chapters 7 and 8, have to do with energy of various types. And today we'll look at work as well. And eventually we'll kind of leave the work behind, although it's closely related to the definition of one type of energy. But I want to start off by talking about some various forms that energy takes, because it's a pretty abstract concept. And sometimes you wonder, how in the world could those things have anything to do with each other? So the first kind of energy we'll talk about is kinetic energy. And kinetic energy is just the energy of motion of a particle. And it's just given by 1/2 mv squared. And so m is the mass of something, v is the speed. And this is not velocity anymore. It's just the speed of the object. And it's always positive, kinetic energy is. It's not a vector, so it has no direction to it, even though the particle's velocity may have a particular direction. The kinetic energy doesn't. It's a scalar. So let's make an important note of that. And many of the types, in fact, all of the types of energy that I'm going to list here are going to be scalars. Now, sometimes we'll use vectors to calculate those things, but the energy itself is going to be a scalar. Also, the V is the speed with respect to what? Okay, we're going to have some kind of a reference frame that will have the speed with respect to, and usually we'll just figure that the Earth is at rest, but we know that that's not actually the case. Anyway, that's the expression for kinetic energy. Other kind of energy that we're going to use is gravitational potential energy. And for this quarter, we're going to stay close to the surface of the Earth. And so for gravitational potential energy, we'll have an expression that looks like this: m times g times h. Well, mg is the weight of an object. H is going to be its height above some reference point. And we're free to pick what reference point that is. A lot of times we'll pick it as the surface of the Earth or the floor of a room or something like that, but we're pretty free to select where that h is going to be measured from. And if the object happens to be sitting down on the floor, for instance, so here's where h is defined to be 0. So here's our mass sitting there. Then it's going to have a gravitational potential energy of 0 at that time. Whereas if it's up here, so it's got some height y above the floor, then it would have a gravitational potential energy of mgy. And we get to pick where things are 0 a lot of times. Now, it turns out that this study of energy and kinetic energy and all of this stuff is just kind of a bookkeeping system. And you can decide where you want the 0 of your checking account to be 0, as long as it's not lower than what the bank says is 0. So you could say, okay, I'm going to set my level at $350. If it falls below $300, I get dinged for it. So I'm going to try to keep it above $350 all the time. And so you might think of that as the 0 of your checking account. And we do something similar with energy. Now, this expression for gravitational potential energy assumes that G is going to be constant. Well, it's not constant. It actually gets smaller with distance. And so if we start moving large distances away from the surface of the Earth, we're going to have a different expression for that. And in that case, we'll actually have an expression that looks like this: minus G times the mass of the Earth times the mass of whatever object we're talking about divided by r, where r is the distance from the center of the Earth. So we're not going to use this expression until next quarter, but that's something that it could look like. There's also something that we'll deal with a bit spring quarter. Whoops, if I could spell. Electric potential energy. And electric potential energy will look like K, which is something that we're going to learn to deal with spring quarter. So don't worry about this expression. That's just what it will look like. K Q1 Q2 over R. Okay, and R is the separation between two charges, Q1 and Q2. Q1 is the amount of charge on one of the objects. Q2 is the amount of charge on another object. And K is actually equal to, it's shorthand for something that looks like this. Epsilon naught is a fundamental constant of nature, and it ends up being about, let's see if I remember right, 8.99 times 10 to the ninth Newton meters squared per coulomb squared, but don't hold me to that because it's been a little while since I dealt with this, but I'm pretty sure that's what the constant is anyway. So anyway, that's another kind of potential energy. And then we could be talking about spring potential energy. And that's something we'll deal with fairly soon here. And that will look like 1/2 kx squared, where x is how much we stretch the spring from its equilibrium position when it's neither stretched or compressed. K is a different meaning than this one here. K is equal to the spring constant. And it depends on which particular spring you've got. I've got a bunch of springs that I bought. Let's see, would have been winter of 1994, I think. So 29 years ago, they're supposed to be identical, but they all have a slightly different spring constant. And we'll talk about what a spring constant is here in a bit, but that's another kind of energy that'll show up. Then you could have kinetic potential energy. Okay, and that's the energy of some kind of a compound and a particular, usually a bunch of that compound. So in general, this would be the potential energy of a whole bunch of molecules or something like that that's built into their chemical bonds. And if you break those bonds and recombine them, you may have other types of energy released. So that's another kind. In general, it's an electric potential energy, but for not just individual point particles, but more complex situations. And a closely related one is food energy. And that's one that is actually a chemical potential energy. It's how much energy can be released by food that you eat and made useful to your body. So that'll depend on all kinds of different things. Heat energy. And what this is the kinetic energy. I'll use a precise scientific term for this. That'd be the kinetic energy of a whole bunch of particles. For instance, the heat energy in a room would be the kinetic energy of all of the air particles in the room. And those air particles are mostly nitrogen, but there's also oxygen and argon and carbon dioxide molecules and water molecules moving around in there, and um, cold viruses that might have come out of somebody's mouth as they're breathing, and just all kinds of stuff. Those are all moving around actually at a pretty good clip most of the time. The average speed of an oxygen molecule at room temperature is in the neighborhood of 500 meters per second. Now they're tiny, so individually they don't have a whole lot of energy, but that heat energy is just going to be this random, disorganized kinetic energy. They're going every which way, and they don't all have the same speed. There's huge variations in the speeds that they have, but that's what heat energy happens to be. And so lots of different things. And then there's one, well, actually, there's light energy. Light carries energy. And Einstein proposed way back in 1905 that light, besides having a wave-like nature, also has a particle-like nature. And people tried to disprove him. A very famous chemist named Robert Millikan in 1915 was trying to disprove Einstein's idea that light behaved as a particle at times, and he ended up confirming it. Robert Millikan is the person who determined the charge on the electron. That may be what he's the most famous for. But the energy of one of these little light particles is, it can be written two different ways. A constant, h, that's called Planck's constant, times the frequency of the light, or hc over lambda, which is c is the speed of light, h is still Planck's constant, lambda is a symbol that we use for wavelength. And you won't have to worry about that symbol or this equation in the class. We'll deal with wavelengths of light next quarter when we study optics. But anyway, that's light energy. And then there's this one, E equals mc squared. Okay, a few weeks ago, you had a lab where you were learning a bit about neutrinos. And one of the things that was brought up in there is, in that film, was positrons, which we write as an E plus. It's the antiparticle of an electron, which is E minus. The electrons and positrons have identical masses, opposite charges. If they happen to meet up, they annihilate each other. You get this little burst of light energy that comes out of there, and you get two photons, two gamma ray photons coming out of this little combination. And each one of these photons has an energy, it'd be an hc over lambda, but for those photons, the energy is equal to the mass of an electron times c squared. That's Einstein's famous equation. Actually, this is Einstein's other famous equation. This is what he got the Nobel Prize for, was this one, and not this one. But anyway, this turns out to be conservation of energy. Before this combination, you had a positron over here that had an energy of mass of the electron times c squared. You had an electron with that same energy. When they combine, poof, they're gone. But you get two photons out of here, each of which has the energy of mass of the electron times c squared. And so that's something that happens. Well, what in the world? Look at all these different weird things. 1/2 mv squared. Okay, that one's proportional to the mass. Gravitational potential energy is proportional to the mass. But then we get to this thing. This doesn't even depend on the mass of the object. It depends on the charge. And a spring potential energy, that depends on the spring constant. So all these weird kinds of energy, all these different expressions, and somehow they're all related to this one thing. And when we study situations, we find that the energy is always conserved. The total amount of energy, it can take all these different forms, but the amount you have before some interaction will be the same as the amount that you have after that interaction. And so we're going to just start getting our feet wet in the next two chapters on dealing with some of these things. So that's a bit of weird stuff about energy. Okay, now for an introductory example on this, I want to just make a graph here. And this graph will be the net force is going to be on the vertical axis that's acting on some object somewhere. And on the horizontal, we'll have just the position of that thing, X. And let's suppose that this net force serves to accelerate the object. Maybe it's, you might have some object that is sitting on a horizontal surface. It's got an applied force. There's a frictional force opposing that. There's the normal force pushing upward and the gravitational force pushing down. But when you add all of those together, this force happens to win. That doesn't make it the net force. It'll be the net force will actually be the vector sum of all the forces that are acting. So if we add all of those things together, whoops, that's supposed to be N here. And then mg is pushing downward, and we'll have a lowercase frictional force here. It'll be kinetic friction, and we'll have an F applied. But let's suppose that in a typical situation, we'd have normal force and mg are canceling each other out, equal and opposite, but they're not third law partners because they're both acting on the same thing. But we have this applied force that's bigger than the frictional force. And so we have a net force. And let's just suppose that it happens to be this much, F net, right there. And this object gets moved from an initial point to a final point, an X final here. Okay, and I want to do kind of a weird little calculation here. I want to calculate the area under this graph. Well, it's not really an area because only one of its dimensions is a length. I've got an F for the other one, but let's just suppose that that area, it's going to equal F net times delta X. So we'll have that there. Now let's think about this. The net force is going to equal whatever mass this thing happens to have times its acceleration. Okay, and we can deal with this one-dimensionally. We'll soon start adding a couple of dimensions to this, but that's okay. And the acceleration will then equal that net force divided by the mass. Now I want to go back. As long as that net force is constant, we'll have a constant acceleration. And I want to go back and consider one of our constant accelerations equations, which is this, v final squared minus the initial squared is equal to 2 times a times delta x usually, but in this case, it'll be x final minus x initial. Doesn't matter. Either one works. X final minus x initial. And the acceleration is F net over m. So I'm going to plug that in here. And I'll get v final squared minus v initial squared is equal to 2 times F net over m times x final minus x initial. Okay, I'm going to monkey around a little bit, multiply both sides by m, and I'd get mv final squared minus mv initial squared equals 2f net times x final minus x initial. And then I'll multiply both sides by 1/2, and I'll get 1/2 mv final squared minus 1/2 mv initial squared equals F net times x final minus x initial. Well, what this thing is, 1/2 mv final squared, 1/2 mv squared is the kinetic energy. And what this represents is the final kinetic energy minus the initial kinetic energy. And what this represents is this area under the curve here, or the area of that box that we happen to have there. Okay. This is the change in kinetic energy, so we could write it as delta KE is equal to this. Well, we're going to be doing stuff like this so much that we've come up with a definition for what things like this are. We call this the net work that is done on the project, on the object. It's the net force that's acting on it. And then we've got these other things that are doing work on it, but this is the net work, and it's two words, not network. So done on the object. Okay. This thing is called the work kinetic energy theorem. And we happen to do it for a situation where we had a constant net force. That's the easiest one that we can come up with, but it'll apply in any situation that the change in kinetic energy of an object will equal the net work that is done on the object. So that's kind of a neat thing. Now, if you start reading chapter 7 in your textbook and you haven't had calculus before, you're going to have something dumped on you right from the start that you haven't seen before. But what the language refers to is calculating areas under curves. And I'm going to move on to that just right away. What if we have I don't know, a curve that looks like this? And here's our force, and here's our position again. And we've got a curve that looks like that. Okay, so we're supposed to calculate the area under this curve. Well, a way that you could do that is if you had a mathematical description, this is supposed to be net force again, of what the net force happens to be, you could calculate the force halfway between 2 points and then figure that that's the average. And if you make these little amounts skinny enough, you could actually have it be fairly constant, but you'd calculate the area of some little slice like that, move over a little bit, calculate the area of the next slice, and do a whole bunch of that stuff. And each one of these, let's just suppose this curve here is the net force as a function of x. Each one of these things is going to look like F net, and we're going to shrink these little interval widths down to dx. And this is F net as a function of x. And the process of doing this is something you learn in second quarter calculus. And they have this symbol that looks like this, and you'd be going from some x initial to some x final. This is an integral, but all it is finding the area under a curve. It looks scary as all get out, but for this quarter, the most complex curve that we're going to find the area under is one that looks like this. Okay, well, if we go from an x initial, if x initial is down here and x final is over here, you're going to be finding the area of a triangle. Okay, you don't need calculus for that. At worst, We may have an X initial that starts here and an X final that ends over here. Well, that's a trapezoid. Again, you don't need calculus because you can turn it into a rectangle. That's easy to find the area of, and a triangle. That's easy to find the area of, and add the two together. So we don't need rocket science for the kinds of areas that we're going to be getting under curves this quarter. Anyway, that's what that will look like. But in general, the net work is going to be something like this, going from some X initial to some X final. This is in one dimension, by the way. And we'll have F net as a function of X times dx. And all of this gobbledygook just means is area under a curve. So whenever you see something like that, if you just think, okay, somewhere there's some kind of a curve that we could draw, and this is just going to be finding the area under it. And so don't worry about it any more than that. All right, now let's consider a situation where we have, here's our X, here's our F net. And let's suppose that F net is pointing in the direction opposite the motion. In that case, F net might be down here. And we'll just suppose for simplicity's sake that it's constant. Okay, so this is going to be a negative value of F net, and then we'll still have our X initial and X final here. In that case, we'll have, actually the F net could be a frictional force. Okay, maybe it's a kinetic frictional force, and the object starts off going in this direction. So this might be V initial pointing in that direction to the right, but there's no applied force in this case. So we'll still have the normal force acting up and mg acting down. I know I had them in different spots before, but this will work. Mg acting down, and the normal force is equal to mg, and this will equal mu sub k times the normal force, which is mu sub k mg. But anyway, it's negative. It's opposite the direction. And in that case, we'll end up with a negative value for this area, which is abstract, but it's not really an area. This is the work done. We get negative work in this case. And so with this definition of work, it's possible to have negative work done. It's also possible to have no work done by a force. So I want to get to talking about how forces can do different amounts of work. And so let's suppose that we displace this object by some distance r, and we look at the work that's done by different forces acting on it. Okay, we've got one weight acting down. We've got a normal force acting up. Okay, and let's suppose that down here we've got a frictional force that's opposing the motion. Whoops, kinetic friction if it's moving. And then we've got an applied force that maybe that's you pushing on this. So this is the force of you doing that stuff. And I'm going to make a little table here. The force and the work that's done. Well, we'll take the force of you. Okay, you will be doing positive work if the object is displaced to the right. Okay, and I'm just going to put the signs down here. the force of the kinetic friction is going to do negative work in this case. It's acting oppositely the displacement of the object. N, the normal force, turns out it doesn't do any work at all, nor does mg in this case. Well, let's see. There must be some way of dealing with this a little bit better. Now, let's suppose that instead of you going like that, maybe you've got a buddy who's pulling on a string or a rope that's attached to this thing. Okay. And there's an angle theta here. Now, the work that's done by whoever's pulling on that string or by the tension in that cord is going to equal, we have to split this thing up into two components. One of them is going to be t cosine of theta, and one is going to be t sine theta. Turns out that component of the tension that's perpendicular to the displacement doesn't do any work, but the one parallel does. And what we get is that we'll get t cosine theta times r, where r is the displacement. Turns out the work that's done by that force is equal to t dot r, the dot product. What that'll give you is t times r times the cosine of theta. T cosine theta ends up being the component of the force in the direction of the displacement. And so when we're talking about little displacements, we're going to say that the amount of work that's done in a displacement like that we'll call dW. And this is where your textbook starts, is by introducing this concept of a force. It's going to equal F dotted with dr. And dr is going to be some little chunk of displacement. And this will be the force while the thing is going through that displacement. And F dot dr. If F and dr are parallel, then you get the magnitude of F, magnitude of dr, cosine of 0. But if they're perpendicular, you don't get any work that's done. So kind of weird things that are going to be going on with this stuff. But that's our basic definition of work. By the way, need to introduce some units here. If work is going to equal F times X or F delta X or FDR, well, our unit of F is the Newton. Our unit of distance is the meter. And so we'll have Newton meters for that combination. We saw before that the net work could equal a change in kinetic energy. Well, what are the units of kinetic energy? We have 1/2 m times v squared. Oh, this is a meter here. This is a mass there. So let's be a little careful with that. But the units here are going to be kilograms times, let's see, v is going to be meters per second. We'd have meters squared per second squared there. What about this? Well, what's a Newton? It's actually a kilogram meter per second squared. And if I multiply that times a meter, I end up with kilograms meters squared per second squared for work as well. And that's the same as the units for kinetic energy. They both have the same units. And these show up so often that they're going to get their own little unit. It's a joule. It's named after, I think it's James Joule, if I remember right. a guy who was doing research back in the early 1800s, maybe late 1700s. And as with the Newton, where it's named after a person, when we write out the unit, we write it in lowercase, but the abbreviation will be an uppercase thing. So capital J is going to be the unit of energy, or yeah, either energy or work. They're both going to have the same units. So new units. And remember, it's a kilogram meter squared per second squared. A Newton is a kilogram meter per second squared. So hopefully by now you've got the unit of the kilogram there kind of embedded in your brain. Okay, someplace I printed off some problems to do on this. And these ones are straight out of your book, although I'll make a file available. I wasn't content with the ones I'd been using before, but let's suppose we'll start off with just a few basic work problems. A 75 kilogram person climbs stairs, gaining 2.50 meters in height. Find the work done to accomplish this task. Okay. Well, let's see. Here's what they're going to have to do. If you look at the forces that are acting on someone, we've got the normal force down there. We have mg acting up. And let's just deal with the vertical stuff. If that person wants to lift themselves up, the force they have to work against, that they'll have to exert a force against, is their weight. And the work in this case is going to be that force, mg, times the height that they raise it by. You could also think of a person as lifting a weight of 75 kilograms, which is going to be hard because that's about 165 pounds, but lifting that weight 2.5 meters in height. So the work in this case ends up being that weight that they have to deal with times the, I'll just call it delta y in this case, mg delta y, 2.5 meters. So 75.0 kilograms, 9.81 meters per second squared, and 2.50 meters, 3 sig figs all the way through. And the work in this case, I don't even know if I have a calculator in here. There's one. Lots of paper stacked up. When I multiply this times that, I get 736 newtons, and times 2.5. Now I'll have Newton meters. I get about 1,840 kilogram meter squared per second squared, but that's a joule. So there we have it. Okay, how much work is done by the boy pulling his sister 30.0 meters in a wagon as shown below? Well, he's exerting a 50 Newton force, but that's not in the direction of the displacement. We've got a 30-degree angle between the direction of the force and the direction of the displacement. So in this case, if I take the work is equal to the force dotted with the displacement, I'll end up with F. Remember, the dot product is magnitude of this, magnitude of that, cosine of the angle between them, cosine of, too bad it's not the sine, because then I could, or that it's not 60 degrees, because then I could do it in my head. But anyway, we'll have the 50 Newton force, the 30-meter displacement, and the cosine of 30 degrees, which makes it hard to do in your head, but that'll be 1,500 cosine of 30, whatever that happens to be. and I get about 1,300 actually. Now, this would be Newton meters, but a Newton meter is a joule. If you break down the Newton, you'll still end up with kilogram meter squared per second squared. So there, a couple of relatively simple problems for that. Something I wanted to do was just to look at some kinetic energy of different objects and the kinetic energy. So we'll start off with a $90-mile-an-hour fastball. Okay, that's a pretty good fastball for, it's not so great in the pros anymore. It used to be kind of the standard, but now it's more like 100 or more for a lot of the people throwing fastballs. But anyway, the kinetic energy in that case is going to be 1/2 mv squared, of course. And mass of a baseball is about 0.143 kilograms. At least that's the mass of one that I had a student gave to me once. There was a gas station giving away free baseballs if you bought more than, I don't know how many gallons of gas it was. And it was back when Randy Johnson was playing for the Mariners. This was a long time ago, way back in the 90s. And Randy Johnson had a good fastball anyway. But I stuck this baseball that the student gave me on a scale and found out that was its mass. Anyway, and 90 miles per hour, we're not going to go for super high precision, but that's just about 40 meters per second. So, and we square that. So the energy of that is going to be 0.5 times 0.143 times 1,600 or 40 squared. And it ends up being about, well, I'll just round it to 110 joules. Okay, kilogram meter squared per second squared on that thing. Let's see. Now let's take a walking person. Something I didn't have you do was measure out a distance on the floor and walk it, but I can make an estimate here. Okay. Let's just say V is equal to 1.5 meters per second. Okay. What about the mass of the person? Let's just pick a person who's, well, let's just say 75 kilograms. Okay. What will be their kinetic energy? 1/2 times, it's still mv squared, using that every time. Well, I'll write it out. $75 kilograms times 1.5 meters per second squared. And see how it compares to the baseball. Okay, for this I get about 84 joules. So a person who's just kind of strolling along 1.5 meters a second, that's not particularly fast. Might be around 3 miles an hour or something like that, but 84 joules. So they've got a speed or a kinetic energy that's comparable to that of a 90-mile-an-hour fastball. Well, let's take a Let's see. 70 mile per hour. Whoops, 70. 1,200 kilogram car. Okay, now if they're going 70 miles an hour, I'll just do a quick conversion here. That's about 31 meters per second. So in this case, 1/2 mv squared is going to equal 1/2 times 1,200 kilograms times 31 meters per second squared. Then it's going to be a bigger number. So yep, look. Okay, I get about 5.8 times 10 to the 5th joules. So that's almost a million joules, 580,000 anyway. So that's a lot more energy. Okay, last one we'll do here is a 1,200 kilogram satellite. Let's see. And in low Earth orbit, need to do something to figure out the speed of it. And going about 7,600 meters per second. Satellite in low Earth orbit completes an orbit in about roughly 90 minutes. And they're traveling a distance about equal to the circumference of the Earth in those 90 minutes, a bit more than that. And so that's how fast they're going. So in this case, it'd be 1/2 mv squared equals 1/2 times 1,200 kilograms times 7,600 meters per second squared. It's going to be a lot bigger number. So, oh, same mass as the car. How about that? Oh, well. That's maybe kind of massive for a satellite. There's a lot of smaller ones than that up there, but that's okay. Okay, in this case, it's going to be about 3.5 times 10 to the 10th joules. So that's actually 3.5 billion joules. So lots. Hang on a sec. I've got somebody at the door. I think I have to sign for something, but it should be less than a minute. Okay, I'm back. All right, let's do some example problems, some other example problems that this is one. Oh, actually, let's take a look at this one. This is also straight out of your book. Suppose the ski patrol lowers a rescue sled and a victim having a total mass of 90 kilograms, that's the sled and the victim, down a 60-degree slope at a constant speed, as shown below. This is key. Constant speed would mean no change in the kinetic energy. Coefficient of friction between the sled and the snow is 0.100. How much work is done by friction as the sled moves 30 meters along the hill? So that would be a distance along here of 30 meters. And then how much work is done by the rope on the sled in this instance? And what is the work done by the gravitational force on the sled? Okay. Do we know what the tension is yet? We don't, probably, but I think, well, maybe not. We'll have the tension acting up in that direction. This is a 60-degree angle. We actually have to make a free body diagram on this. And it's 60.0 degrees. So 3 sig figs on that. There's our tension. We've got mg acting downward. Let's see, we'll have a normal force. And we'll also have a frictional force that's pointing in the same direction as the tension. And I'm going to write it F sub K, and it's just going to be up the hill there. Okay. This is going to be 30 degrees here. If that's 60 degrees up there, that way 30 plus 90 plus 60 is 180. So we'll have that. Any suggestions for a coordinate system here? I've got 3 forces that if I use a strongly tilted coordinate system, I won't have to mess around with components for, and the only one I have to worry about is mg. So I'm going to let x point up the hill and n point perpendicular, or not n, y point perpendicular to the hill. And then I can say things like F sub A, the force of kinetic friction, is going to equal whatever its magnitude is in the I hat direction. T will also point in the positive I hat direction. N is going to point in the Y hat or J hat direction, so it'll be its magnitude in the J hat direction. And mg is the only one I have to mess with, and it's going to point negative in both the X and the Y direction. But this will be in cosine of 30 degrees, and this will be in sine, or mg. Mg. There we go. And this will be mg sine of 30 degrees. Okay, so mg is going to look like this. Oh, you thought you were leaving this stuff behind. Alas, minus mg cosine of 30.0 degrees in the I hat direction minus mg sine of 30.0 degrees in the J hat direction. Okay, well, it says it's going at constant speed, and that means the sum of all the forces is going to equal 0. There's no acceleration. Well, that means in the I hat direction, I'll have t plus f sub k minus mg cosine of 30.0 degrees is equal to 0. In the j hat direction, I'll have n minus mg sine of 30.0 degrees is equal to 0. And this lets me know the normal force. The frictional force is going to equal n times mu sub k. So I think we can figure out what the tension is. But actually, the first thing it asks is how much is work? Yeah, no, where is it? A, how much work is done by friction as the sled moves 30.0 meters along the hill? Well, the friction is that way. it says they're lowering the rescue sled and the victim. So the displacement is down in this direction and friction is up. That means it's exactly opposite there. So for the first part, we're going to have the work done by friction is going to be, actually, if I take the frictional force, F sub K, and dot it with the displacement, which we didn't write down the displacement yet, but the displacement in this case is going to be down the hill. That's the negative X direction. So minus the magnitude of the displacement, which is 30 meters, 30.0 meters in the I hat direction. Okay. So that work done by friction is going to be whatever the magnitude of the frictional force is. Here's the normal force. Mu sub K times N in the I hat direction, dotted with D, just D in the I hat direction, or in the minus I hat direction, minus D in the I hat direction. And I hat dot I hat is 1. I'll end up with a negative amount of work minus mu sub K times N times D is what it ends up being. And N was actually mg sine of 30. So the work done by friction in this case will be minus mu sub K mg sine 30.0 degrees, and D, 30 meters there. So plugging all those numbers in, I don't know what we're going to get. Mu sub K was 0.1. I'm not going to rewrite it here. I'm running out of room anyway. 90 kilograms was the mass, 90.0. 9.81 meters per second squared. Sine 30, that's 1/2, I believe. But I'll go ahead and stick a 5 in for it. And the displacement, which I forgot again, 30 meters. And I'll get minus 1,320. And it'll be joules. It's a force times a displacement, so it'll be Newton meters or joules. Now, because I'm rounding this to 3 significant figures, we may end up with a little bit of round off error when we're all the way done with this thing, but we'll see. The next part asks how much work is done by the rope on the sled in this distance. Well, that's the tension in the rope. And the tension in the rope I have to calculate. It's going to equal mg cosine of 30.0 degrees minus the frictional force. And so a little bit of work. This is, now I have to be careful about using the word work because it's going to have loaded meanings after this. Anyway, 9.0 kilograms times 9.81 meters per second squared times the cosine of 30 minus F sub K is going to be mu sub K, which is 0.100, and I'll just put a note under there. That's mu sub K times the normal force, which is, 90 kilograms again, times 9.81 meters per second squared. That's the mass. And this one we have to multiply by the sine 30. Okay. And so the tension um, isn't the full part of the weight of the person that points down the hill, because the friction is actually helping to slow down that descent a little bit. So and I get about 721 newtons. So the work that's done by the tension, it's still opposite the displacement. In fact, if I write this, it'll be that thing. The work that's done by tension, W sub T is equal T dot D, or the magnitude of T, the magnitude of D, cosine of the angle between them, which is 180.0 degrees, and that's -1. So we'll have 721 newtons with a minus sign here, times those 30.0 meters. Should work out. And I get about minus 21,600. Oh, that was small. Yeah. Joules, Newton meters. Okay. The last part asks, what's the work done by the gravitational force on the sled? That's not the last part yet, but the work of gravity, if I look at this, the displacement's downward. The component of gravity that's in that direction is mg cosine of 30 degrees, or I could write it as the work of gravity is going to be mg dotted with the displacement, which would be the magnitude of mg, the magnitude of the displacement, and the cosine of the angle between those two vectors is cosine of 30.0 degrees. So we will have 90 kilograms, 9.81 meters per second squared, 30.0 meters, and the cosine of 30.0 degrees. So the work done by gravity and I get 22,900 joules. And then it asks, what's the total work done? Well, I add these three together. I take WG plus WT plus WF, and I'll get 22,900 minus 21,600 joules. These are all joules. Don't forget units. Minus 1,320. And let's see what I get. Now I've got these things stored in my calculator. So I actually get minus 1 joules for the total work done, but that's lost in round off error. Okay, since I've only got these things to 3 significant figures, I essentially get 0. And if I could have kept more significant figures, I could have gotten this to add up exactly to 0. So if something is traveling at constant speed, the total work done on it will equal 0. Okay, that's probably enough for one day. And tomorrow we can go a little bit farther with this stuff, and we'll look at some other types of problem, and we'll also look at spring potential energy for tomorrow. Does anyone have any questions? I didn't see any messages in here. Didn't have a whole lot of.
Yeah, I got one question.
Okay.
So going back to our diagrams that you drew earlier when we were talking about the integrals.
Yes. Like
Yeah, so
that one, maybe.
uh yeah, that one, but it was the ones you drew after that. I just didn't know the integrals was easier to describe.
Hmm.
It was you did F net 0 and F net below the 0.
Let's see. Huh. Oh, now I can't remember where I put them. Let's see. Wasn't on that page. This one? Nope. That one? Or,
No, not quite.
okay. Huh. Let's see. Here are the ones where I did some of those.
It was similar to that one on the left, but
Uh-huh.
you put at the origin you put 0, and then you put an F net
Oh,
below.
where I had
Yeah,
a negative one.
yeah. It was negative work. It
Oh,
was a negative work
that's this
diagram.
one. Yeah. Um, nope, that's not it. Okay, man, where did I keep track of all these things? Oops, that's yesterday's anyway. Um, I know what you're talking about. Oh, I bet it's on the back of this. Yes.
Yes, that one. Okay,
Yep.
so can you kind of explain that diagram on the left a bit more? Because
Okay.
we would have F net below 0, and is that
Yeah.
just
What this would mean is that this is positive is up on this thing and it's below 0. And that just means that its direction is it's pointing in the opposite direction of the displacement. So if the object is moving to the right, the force would be pointing to the left.
okay?
And it would be like a frictional force. It actually acts to slow the object down. And a
Oh,
force,
gotcha. Okay, so just depending on whichever, like if you had more force going in the opposite direction of your displacement, then it would look similar to the graph on the left.
yeah, yep, you'd be
Okay,
slowing it down.
gotcha.
And
Okay,
forces, if you have a net force that is speeding the object up, then it's up here in the positive direction. It'd be up on this part and you'd have positive work done. But if the force is acting to slow the object down, you have negative work done. And that means that the change in kinetic energy is going to be negative. So,
okay, that makes sense. And then on that bottom diagram for the vector r, that isn't a force, is it? That's just representing the direction of the displacement.
yeah, it's representing the displacement
Okay,
actually. So it'll be a distance vector or a displacement vector. I guess I
okay.
could use a D for that instead for
Yeah, you
displacement.
just wrote the R and then you wrote the D later on, and I was like, okay, I'm just gonna verify to make sure it's the same thing.
Yeah. Yep.
All right, thank you, Professor.
You bet. Any other questions? Let's see. All righty. Well, I'll see you tomorrow, and I have a bunch more stuff to post here today. So uh, I'll have the example problems I started today up there. And and then some suggested problems in the back of the book or in the chapter to give a shot.
All right.
Okay.
Thank you.
Yep. See you all tomorrow.